one dealing with molar specific heat. Consider this. Let's say we have a PV diagram. We have an isotherm, which defines a state of a system, the internal energy. And if we were to go from one internal energy to another, our change in internal energy from one isotherm to another would be the same. In other words, we're strictly changing our state from one to the other, and how we got there to the different state won't matter. There are several processes that can change the temperature and the state of a system, and for all these processes that would change between these states, our change in internal energy will be the same. However, the heat added could be different. It's going to be different for any particular path that we choose, and the work done on the system will also be different by the first law of thermodynamics. So, what's important here is that the heat associated with a particular change in temperature is not unique. So if you say that you're heating something up and you heat it with a certain transfer of energy, that doesn't necessarily take you from one particular state to another, because work is involved as well. So really, a change in state, a change in temperature is associated with a change in internal energy, but not necessarily the transfer of heat. Consider two processes that occur quite frequently. We define the heat added at constant pressure to be equal to the number of moles N times the molar specific heat at constant pressure times the change in temperature. This is just a definition, knowing that we're going to have a definite change in temperature, a definite amount of moles, so we can now define the heat associated with that process. And the heat added at constant volume will be defined to be the number of moles times the molar specific heat at constant volume times the change in temperature between states. So the red line is constant pressure as we're going from one state to the next, and the blue line is at constant volume as we go from the same state to the next state. These molar specific heats, C sub P and C sub V, are the molar specific heats at pressure and volume respectively, and they are definite values that we can calculate. The change in internal energy between any two isotherms will be constant because the temperature change will be constant. So no work is done at constant volume. By the first law of thermodynamics, we can get rid of the work at constant volume, and our change in internal energy will then just be equal to this heat added to the system in that particular case. Hence, our change in internal energy will be equal to, at constant volume, the number of moles times the molar specific heat at constant volume times the change in temperature, just like the heat added to the system. Now, this was calculated at constant volume. However, since the change in temperature is going to be constant between any two states, and our change in internal energy will be the constant between any two states, C sub V is a constant, number of moles is a constant. This is a constant for any change between any two isotherms. We can use this for any particular change in energy between two isotherms. So actually, even though we define the molar specific heat at constant volume for that condition of constant volume, this particular equation can be used for any change of internal energy between states. Very, very nice. So we can use it for any transition between two isotherms because our change in internal energy is a constant. Since for monatomic gases, we have from earlier from the ideal gas law and our calculation with the Boltzmann constant, we have the change in internal energy is equal to 3/2 number of moles, gas constant R, change in T. Comparing this to what we just got, we have that for all change in internal energy, number of moles times the molar specific heat at constant volume times the change in temperature should equal this value as well, 3/2 nR delta T. Get rid of the number of moles, get rid of the delta T's, and we have that the molar specific heat at constant volume for a monatomic gas is 3/2 times the gas constant R. How about that? So we have a definite value for the molar specific heat constant volume for monatomic gases. Here's the molar specific heat for hydrogen, which is actually a diatomic gas, as a function of temperature. At low temperatures, we have that the molar specific heat is 3/2 R. Then as we raise the temperature, hydrogen is a diatomic gas, so we actually introduce the 2 extra degrees of freedom of rotation as the temperature goes up. So that molar specific heat goes up to 5/2 R. And then as we introduce 2 more degrees of freedom for vibration, it goes up to 7/2 R. But at low temperatures, this diatomic gas of hydrogen, H2, acts like a monatomic gas with a molar specific heat of 3/2 R. Also, if we have an expanding gas at constant pressure, we would say by the first law of thermodynamics, change in internal energy is equal to the heat added to the system plus the work done on the system. And putting in our numbers, we know that for any change in internal energy, we're going to have N molar specific heat at constant volume delta T. For a constant pressure, our heat added is going to be N molar specific heat at constant pressure delta T. And if the pressure is constant, only changing the volume, we have that our work done on the system will be a negative constant pressure change in volume. We're going somewhere with this. Note for our ideal gas, PV equals nRT, so P delta V equals nR delta T. We're going to substitute this in for ideal gas into this previous equation. We now have this. Number of moles, C sub V delta T equals number of moles C sub P delta T minus N number of moles R delta T. Number of moles cancel out. The delta T's cancel out. And I'm left with molar specific heat at constant volumes equal to the molar specific heat at constant pressure minus our gas constant R. Or in other words, the molar specific heat at constant pressure is equal to the molar specific heat at constant volume plus R. What a neat result. So for monatomic gases, the molar specific heat at constant volume is 3/2 R, which is 1.5 times our famous gas constant, 8.31, 12.5 joules per mole per Kelvin. The molar specific heat at constant pressure is an R added to this. So it's going to be C sub V plus R, 12.5 plus 8.31, 20.8 joules per mole per Kelvin. That's for monatomic gases. For diatomic gases, the molar specific heat at constant volume is 5/2 R at room temperature. That's going to be 2.5 times 8.31, 20.8 joules per mole per Kelvin. And the molar specific heat at constant pressure will be R plus this, which will give us 29.1 joules per mole per Kelvin. So with these new definitions of the molar specific heats, we're armed with these new tools. Let's revisit our PV diagrams. We know that if we have a PV diagram and we have a process on this diagram, the area under a PV diagram plot is the work done on the gas. Negative if we're moving to greater volume, because then the gas actually is doing work. And positive if we're moving to lesser volume on this diagram, because there would be work done on the gas. So in this particular case, going to a greater volume, negative work done. If the path is cyclic, the change in internal energy would be 0. The heat added would be equal to the negative work done according to the first law of thermodynamics. And the net work done as we go clockwise on this path will be the negative of the area enclosed by the cyclic path. And the heat added will be the positive of that area if we're going clockwise. And then everything will be reversed if we go counterclockwise. Reviewing our PV diagrams, continuing this, if we look at isotherms, our change in internal energy is equal to 0. So in that case, by the first law, our heat added will be equal to the negative work done on our gas. So for isothermal, that actually will be the work done will be equal to the negative work done underneath this graph. And we've calculated that before. Change in internal energy 0, Q is equal to negative W. And in particular, for ideal gas, the work done as we go from lesser volume to greater volume, or from any initial volume to final volume, is nRT natural log V initial over V final. I guess if one were greater than the other, the natural log will still sort it out. And the Q is the negative of this. So Q will be equal to nRT natural log final volume over initial volume. Change in internal energy, of course, is 0 for isotherm. For isovolumetric or isochoric, the work done is 0 because we're not changing our volume. And in that case, the heat added will indeed be equal to the internal energy change of the system. Here's an example. At constant volume, we're simply going initial pressure to final pressure, no area underneath that graph, so no work done in this graph. So work done is 0. Change in internal energy is equal to the heat added to the system. Now we know in particular that the change in internal energy will be equal to N C sub V delta T, where C sub V is the molar specific heat at constant volume. And in this case, we have constant volume, so Q is also equal to N C sub V delta T. Work done is 0. For isobaric, consider this. We have Dracula, ooh, scary, and we have the Wolfman, ooh, equally scary. We would say that they are isobaric. Iso meaning the same, baric meaning, I'm kind of confused here. This is not isobaric. This is isobarbaric. Isobarbaric. Equally scary. Okay. What is isobaric? Now, isobaric, we have constant pressure. Work done is equal to negative pressure times change in volume. We have a change in internal energy equal to N C sub V delta T. And our heat added at constant pressure is N C sub P delta T. We needed something to break that up. So here's our PV diagram. At constant pressure, the work underneath this graph, or the area underneath this graph is equal to the negative work done. And as we're going from initial to final volume, we're actually going to cross isotherms. So we're going to change our internal energy state. So in particular, work is equal to negative P delta V. Change in internal energy for any change of state is going to be N C sub V delta T, as we proved earlier. And for this particular case, our heat added is going to be N C sub P delta T. So that will be our three variables for that. For adiabatic, in an adiabatic system, you can't add or exchange heat to the system. It's isolated, either by the process or by its insulation. So the change in internal energy will equal the work done on the system. So, in particular, we might have a change in internal energy as we adiabatically expand. That actually will be a negative change in internal energy as our volume is getting larger, because we'll have the work will be equal to a negative area underneath this graph. So as the gas expands, internal energy goes down. Q, heat added, is 0. Change in internal energy is equal to the work done on the system, which is a negative value. Work on the gas is negative. Curve crosses from a higher state to lower state, higher isotherm to lower isotherm, higher temperature to lower temperature. So in particular, no heat added. Change in internal energy is equal to NC sub V delta T as always. And the work in this case would be equal to NC sub V delta T, just because it's equal to the change in internal energy. As we go from a higher temperature to a lower temperature, this delta T will be a negative value. All right, one of the things we're going to be interested in one of these processes in particular, will be the ratio of our molar specific heats. We call that gamma. We define the ratio of molar specific heats as being equal to our molar specific heat at constant pressure divided by our molar specific heat at constant volume. Gamma is equal to C sub P over C sub V. For a monatomic gas at room temperature, that is 5/2 R over 3/2 R. R's cancel out, and that will be 5 divided by 3, or 1.67. This is an excellent agreement for monatomic gases. Note for diatomic gases at room temperature, our C sub P is actually 1 R greater, 7/2 R, and so is our C sub V, 5/2 R. So for diatomic gases, this is 1.4. Also an excellent agreement at room temperature. So here is some graph of some monatomic, diatomic, and polyatomic gases. The gamma for monatomic gases at room temperature, 1.67. Diatomic gases like hydrogen, nitrogen, oxygen, carbon monoxide, chlorine, 1.4. The monatomic gases are noble gases: helium, argon, neon, krypton. Polyatomic gases: carbon dioxide, sulfur dioxide, water, and methane, 1.30 for these. So excellent agreement for these gammas for these gases. Here we have an adiabatic process, one in which we're very interested in, because many of the processes that we use are adiabatic, where there's no heat exchange. And in this process, if we were to expand initial to final, our temperature would go down as we go from a higher state, temperature state, to a lower state. In this expansion, our final temperature is less than our initial temperature, so the gas will cool. And if we were to go the other way, from a initial temperature and compress it to a final temperature, our gas actually would heat up as we're going with no heat, or gas would actually increase in temperature with no heat added, but because of the work done on the system, there will be energy added to the system and the temperature will go up. For all adiabatic processes, it can be shown that our initial pressure times our initial volume to the gamma for that gas is a constant. That will be equal to our final pressure times our final volume to the gamma. We're not going to prove this here, but we're going to use this here. So this is a formula very useful only for adiabatic processes. So we have for adiabatic processes an ideal gas, PIVI to the gamma is equal to PFVF to the gamma. We also know for our ideal gas, we have the ideal gas law. P initial, V initial over T initial is a constant as well. That's equal to P final, V final over T final. If we divide the first equation by the second equation and then multiply by 1 on both sides, so we get rid of a P initial on the left and a P final on the right, and then we're going to multiply by T initial over T initial on the left and T final over T final on the right. Let those cancel out. We get a similar expression. T initial, V initial to the gamma minus 1 is equal to T final, V final to the gamma minus 1. Only for adiabatic processes, but this relates our temperature and our volume initially to our temperature and volume finally. So it could be a very useful formula as well. So summary for adiabatic processes, P initial, V initial to the gamma is P final, V final to the gamma. We just proved T initial, V initial to the gamma minus 1 is T final, V final to the gamma minus 1. And similarly, through some algebra, we can also prove that T initial, P initial to 1 minus gamma over gamma is equal to T final, P final to the 1 minus gamma over gamma. So gamma is going to be a very important quantity to know for the gas, and this will allow us to relate two of our state variables to the third state variable if we have an adiabatic process. And finally, as always, for these gases, the ideal gas law applies. So PV over T is a constant. P initial, V initial over T initial is equal to P final, V final over T final. Let's try this out in a problem. 1 mole of helium gas expands adiabatically from 2 atmospheres pressure to 1 atmosphere pressure. If the original temperature of the gas is 20 degrees Celsius, what is the final temperature of the gas? All right, so we know our initial pressure and we know our final pressure. We know our original temperature is 20 degrees Celsius. We need to convert that immediately to Kelvin. So we have an initial temperature of 20 degrees Celsius, which is 293.15 Kelvin, and we want to find the final temperature. Well, we know our two pressures, we know our initial temperature. We can use this adiabatic relationship to find the final pressure. This gas is helium, so it's monatomic at room temperature, 1.67. So we have T initial, P initial to 1 minus gamma over gamma is T final, P final to 1 minus gamma over gamma. Let's solve this for T final. T final will equal T initial, P initial divided by P final, 1 minus gamma divided by gamma. That's going to be 293.15 in Kelvin. Initial pressure was 2, final pressure is 1. Atmospheres cancel out, so it doesn't really matter what our units were if they're the same. 2 over 1. 1 minus 1.67 divided by 1.67. So that's 293.15, 2 to the negative 0.67 over 1.67, whatever that is. If you do that on the calculator, it's going to give us 222 Kelvin, which we can convert back to Celsius. Subtract a 273.15 from that, and we get a negative 51.2 degrees Celsius. So that will be the final temperature of our gas. We expanded it from a smaller pressure to a lesser pressure, or a greater pressure to a lesser pressure, expanded it, and in that sense we cooled the gas to a minus 51.2 degrees Celsius. This could be a good refrigeration system. Okay, try your hand at the problems for this section dealing with